Let's take a look at the quantum numbers and orbital notation for atoms with more than one electron. The Schrödinger equation has been solved for the hydrogen atom, which has one electron. But as it turns out, the solutions for many electron atoms are it's impossible to solve completely, and so we have to use approximations for the hydrogen atom. Okay, and what happens in this case is we lose degeneracy, and what degeneracy means is across, in the context of quantum mechanics, is for the hydrogen atom. If you remember, I'll draw the hydrogen atom energy levels in this subset here. We had energy increasing on this axis. We had 1s and then 2s and 2p. There was 1. And then we had 3s, p, and d. 1, 2, 3, 1, 2, 3, 4, 5. And all of the subshells and orbitals were of the same energy within a given shell. But when we have a many electron atom, we lose that degeneracy. This would be considered degenerate, and our subshells shift. So now the 2s is of lower energy than the 2p, whereas in the single electron situation, the 2s and the 2p were of the same energy. So because of this, for the many electron atoms, we actually have to add a fourth quantum number called the spin quantum number. And the reason why is because it's abbreviated M sub s, is because of the Pauli exclusion principle states that in a given atom, no two electrons can have the same set of four quantum numbers, yet two electrons can occupy a single orbital. So we have to add this other quantum number to satisfy this condition. Okay, so each orbital can only hold up to 2 electrons, and they must have an opposite spin. And remember again, in the case of hydrogen, which is all we've looked at so far, we would have the 1s, the 2s, the 2p, and we could say the electron could reside here, or if it's not there, it could be an excited state, it could be here, and relax back down to there, and whatnot. So we were only always dealing with one electron. But in the case of the many electron atom, then we have to deal with the fact that we could have more than one electron, up to 2 in each orbital, and they need to be described by a set of 4 quantum numbers now. Okay, so that's the result of the many electron atom. So, and then let's practice this. State the ground state electron configuration and the associated quantum numbers for the element beryllium. Okay, beryllium has an atomic number of 3, which means it has 3 electrons. So if we follow the Pauli exclusion principle, we're going to fill the electrons from the lowest available energy levels, the 1s. So we're going to put 2 in the 1s. We have 3. The next electron is going to go to the next higher energy level, so it'll go into the 2s. So if you write the electron configuration then for beryllium, it's going to be 1s, 2s. That's one way of writing it. Or you could say 1s, 2, indicating that there's 2 electrons in that orbital. Whoops, 2s, 1. Okay, so either one of these would be electron configuration orbital notation. And then if we want to then write the associated quantum numbers for these for this orbital notation, then we for the 1s, the quantum numbers associated for the 1s would be 1, 0, 0, and one of the electrons, the spin would be plus 1/2, and then for the other electron, it could be 1, 0, 0, minus 1/2. So there's a set of 4 quantum numbers that could describe, say, this electron, and then another set of 4 quantum numbers to describe, say, that electron, and then we need a set of 4 quantum numbers to describe the 1 electron in the 2s, and that would be 2, 0, 0, and you could say plus or minus 1/2. It doesn't matter. You just have to pick one. So in this case, I'll just say plus 1/2. So those are the 3 sets of 4 quantum numbers that would describe the 3 individual electrons. Again, each electron requires a set of 4 quantum numbers, unique quantum numbers, to describe its energy and location, probable location, to describe it fully. Okay? And then the next question here, it says the 4 quantum numbers for an electron in a beryllium atom in a certain excited state are n equals 4, L equals 2, m equals 1, m sub s equals plus 1/2. What type of orbital is this electron located? All right, so if it's 4, then it's the orbital with energy level 4. L equals 2. Again, when L equals 0, it's S. When L equals 1, it's P. When L equals 2, it's D. So this particular electron is in a 4D orbital, but we don't know which one it is. It's in one of the 5 available orientations, and so you could put it like that: 1, 2, 3, 4. Wait, 1, 2, 3, 4, 5. Whoops, put 6 lines. And so there's 1 electron in this orbital, and you just put it like that. So it doesn't look any different than if we had an excited hydrogen atom. The notation would look the same. In this case, it's just we're just saying it's not in the ground state 1s2, 2s1, but in this case, this particular electron has been promoted to an allowed state, which happens to be the 4D orbital.